Hello and welcome back to our course on drone surveying. Today we will study about flight planning for drone survey and its limitations. So let's start with a motivating example. You are surveying a 50-hectare construction site to create a 10 centimeter ground sampling distance map. So you plan an afternoon drone flight, but mid-mission the drone battery runs low before even completing the mission. All regions were not covered by overlapping photograph and the survey was rendered incomplete. So could there be a systematic way to achieve this? For example, you wanted a 10 centimeter ground sampling distance map. So what is the flying height for the drone to achieve that? For example, you did an afternoon drone flight. So is this a good time to do a drone flight? Because the winds may be high, there may be long shadows. Your drone battery also run low before even completing the mission. So could we have estimated what is the flight time and compared that with the battery life, whether it is suitable for the mission or not? And similarly, all regions were not even covered by overlapping photograph. So what are the overlapping percentage of the photograph that is needed for doing a drone survey? So understanding all this falls under flight planning. Understanding the flight planning parameters and understanding its limitation will help us achieve the drone survey objective efficiently and safely. So through this lecture today, we will learn about flight planning and its need, flight planning parameters, ground sampling distance, overlap, and number of photographs, how they are related with each other, and what are the limitations of flight planning. So flight planning is the process of designing and optimizing a drone's flight path and operational parameters to ensure complete, accurate, and safe data acquisition over the target area. And it starts with one thing: what is the end product and what is the specification of the end product that is desired. So end product can be point cloud, it can be a digital surface model if you're interested in the height, or if you're only interested in the 2D propositions, it can be orthophoto. At the same time, the specifications can be in the sense of what's the ground sampling distance which is required, what is the positional accuracy which is required, what is the area, what is the shape of that area that needs to be covered, and so on. So flight planning helps us achieve data quality and consistency so that we have consistent coverage of the data and quality in all over the region of interest. It helps minimize the flight time and battery consumption, therefore minimizing the overall cost associated with the survey project. It also helps enforce geospatial accuracy and control through locations of ground control points. It also helps in safety and risk mitigation as well as regulatory compliance so that your drone does not fly into some kind of zone which is near the airport, near some military installation or some other critical infrastructure. And finally, with flight planning, we can save it all as a file which will help us in reproducing the mission, let's say after 6 months or after 1 year when mission maybe need to be repeated. So the main planning parameters that we have are the region of interest and geofence, what is the desired ground sampling distance, what is the drone type that is available to us, what is the camera and the lens, which essentially means what is the sensor size and the focal length that is available to us, what is the desired photo overlap, if there is any wind, then what is the speed and what is the direction of that wind, what is the maximum ground speed of the drone, and what are the locations of ground control point. With these parameters, we can derive some more parameters, which are the size of the region of interest, the shape of region of interest, whether it's a regular polygon or whether it's a long corridor or whether it's in some irregular shape. It can also be the flying height above ground level, whether we also need to inculcate any terrain following feature. It is also alignment of waypoints, how they are aligned or how they are situated with respect to each other. What is the number of flight lines? What is the number of photographs taken per flight line? And what is the time interval per photograph? In addition to this, what is the direction in which the flight should be situated, keeping in mind the wind direction? And by combining or by calculating all these, we get the flight plan for UAV. Now, once we receive the flight plan for UAV, then this flight plan is loaded into the UAV's flight controller, which allows the UAV to fly autonomously following a pattern, get photographed at set locations, and therefore meet the user criteria efficiently and safely. So the main steps involved in the flight planning process, which we are going to cover today, are as for the inputs, we need to define the region of interest as well as the geofence around or in the region of interest. At the same time, we also need to define what is the UAV that is available to us and what are the camera parameters available to us. Based on this, we find a relationship between the ground sampling distance, flying height, camera focal length. We also find out relationship between the image overlap as well as ground control points and the camera angles. We also find out relationship between the waypoints for survey grid pattern. And finally, we also try to understand how is the flying velocity affected by the wind velocity. And based on this, a pre-flight simulation can be performed, which can then be deployed into the drone. So let's start with the first concept and understand the relationship between flying height and ground sampling distance. So in this setup here, we have the height above ground level given by capital H. We have the drone fitted with a camera with a focal length of f, and this camera images 2 points AB, the distance between which is capital AB, and this distance capital AB is shown as distance small ab in the image. And all these parameters h, f, small ab, capital AB, they are related through image scale. So image scale is defined as image distance by ground distance, we are already aware of that, and which is equal to focal length by flying height. This can be shown by similarity of triangles, we can all find that. And this is equal to small ab by capital AB. So next we have the ground sampling distance, which is defined as the distance between pixel centers measured on the ground, which is dimension of the pixel in real world. So let's try to find out relationship between scale and ground sampling distance. So we just saw that scale is nothing but photo distance by ground distance, or we can also write photo distance by ground distance is equal to h by f. This is based on the definition of scale that we have. We can also say therefore AB is equal to h by f into small ab, and if we assume that small ab is referring to the sensor dimension, then capital AB refers to the size of the image on the ground, and if we divide both sides by the number of pixels in that dimension, so we divide this by number of pixels both sides, then this is equal to nothing but the ground sampling distance. And we can see that if we have a higher flying height, then ground sampling distance increases, and if we have a smaller f, then also ground sampling distance can increase. On the other hand, if we have larger f, that means if you are using a zoom camera, then ground sampling distance can even decrease. And usually when we want a survey in which we want to see very small details, very fine details, then we want to go for small ground sampling distance. For example, a finer ground sampling distance of 1 centimeter per pixel, this is used in cadastral survey where we want to monitor the boundaries of a property. However, if we have only agricultural application, we just want to use the UAV for spraying on the crop, then even a coarser ground sampling distance of 10 centimeter per pixel may be good enough. So ground sampling distance, based on this, the surveyor can decide what should be the flying height of the drone, what should be the camera sensor width, what should be the focal length and image resolution. So let's solve an example to better understand this concept. So a drone survey is performed from a height of 80 meter with a 16.8 megapixel camera. So in this 16.8 megapixel camera, it is given it has 5472 pixels in the width direction and 2073 pixels in the height direction. So basically this is how the image looks like. And these are the number of pixels. It has 5472 in the width and 2073 in the height direction, with a sensor size of 13.2 millimeter width and 8 millimeter height, and carrying a lens of 8.8 millimeter focal length. So what will be the ground sampling distance which will be obtained? So we just saw that ground sampling distance is equal to h by f, the flying height. So we have a flying height of 80 meters divided by the focal length, which is in this case given as 8.8 mm, multiplied by the sensor dimension. So sensor dimension is 13.2 mm in the width direction. So it is 13.2 mm in the width direction divided by the image dimension, the number of pixels. So, number of pixels of width is 5472 divided by 5472. So, when we solve for this and when we put appropriate units, we get the ground sampling distance in the width direction is equal to 2.2 centimeter per pixel. That means every pixel has a size of 2.2 centimeter on the ground. Similarly, ground sampling distance in the height, when we calculate that, it comes out to be 3.5 centimeter per pixel. So, every pixel here has a size of 3.5 centimeter in the height direction. Height here does not mean elevation, height just means width and the height again in the xy plane. So, moving ahead, next let's understand the setup for acquiring overlapping images. Why do we need them? So, using overlapping images, we can estimate heights of objects which can then be used to generate a stereo model or a digital elevation model using the drone images. And we are able to estimate heights or depths of objects because any object when seen in images acquired from two different camera stations, so its position will appear to have shifted with respect to image center. And this apparent shift, so in this image it may be this object will appear somewhere here, in this it will appear somewhere here. So, this shift, apparent shift is known as parallax, and the parallax allows us to measure height or depth of objects. So, let us look at this setup. In this setup there is UAV at exposure station L1 which is moving to exposure station L2 in the right side. So, distance between the two exposure stations, basically exposure stations refers to point from where images are acquired. So, distance between L1 and L2 is known as, or distance between the exposure station is known as airbase, and often it is denoted by capital B. And we have a building of height capital HA. So, the top point of this building capital A is visible as small a in the left image and small a dash in the right image. And we can see that compared to the center of image, in the left image the small a appears on the right, and in the right image small a dash appears to the left. That means if we just look at two images, then it will appear that the object A, this top of this building, has shifted from the right side of the image to the left side of the image, and this is the parallax. And you can also see that this parallax is related with the height of the object. So, taller the objects, more parallax we see. So, it is important to note here that a point must be visible in at least two images to calculate its elevation. That means an image must have an overlap or a common region in what they capture, and only for the common points visible in the overlapping region, only their height can be calculated. So, let us look at this setup now. We have this drone flying at exposure station 1. So, this is where it is taking photograph, focal length is f, flying height above the ground is capital H, and the terrain is situated at small h above the datum, and there are different objects. And this is the image acquired by the drone at exposure station 1. Now, the drone moves to exposure station 2, and as we saw, distance between the exposure station is called as airbase. Then at exposure station 2, again the drone will acquire an image. Now, we can see that between these two images there is some overlap, the image which is acquired at exposure station 1 and 2. So, this overlap is shown in yellow, and this is known as overlap, or it is also known as end lap, and the distance between the exposure station 1 and 2 is known as the airbase. Then again the drone moves to exposure station 3 and a new image is acquired. Again we can see the image that is acquired at exposure station 3 has some overlap with the image acquired at exposure station 2. One more thing can be noticed here, which is that the image, the portion of image which is not overlapped. For example, if we look at this first image, so this portion of image is not overlapped, right. So, this portion of image which is not overlapped, that distance is same as the airbase. So, we will use this property that the non-overlapping portion, that distance on the ground is same as the airbase later on. Okay, so the drone moved from exposure station 1 to 2 to 3, and now the drone will take a turn, and again it will acquire an image. Now, we can see that this image, it has an overlap in the side direction. So, this portion is known as the side lap, and more images will be required. And now you can see that this fifth image has both overlap in the forward direction as well as side lap in the side direction. So overlaps are needed in both directions to guarantee stereoscopic coverage throughout the site, and along the flight direction we have end lap or overlap. They are used interchangeably and they are needed for parallax, and between adjacent flights we need side lap to avoid missing bits, and overlap and side lap they are kept at least 60% and 40% respectively. So what happens if we don't have enough overlap? In that case, we will see that some portion has been missed out. So in those portion, there is no image which is covering. At the same time, there is some portion which does not even have any overlapping image. That means for such portions, we cannot generate a 3D map. So 3D map will only be possible in this case for these square patches. So that will not lead to any useful map. On the other hand, we may have a situation of excessive overlap in which the drone is moving very slowly and there are so many, and the overlap is almost 95%. So this will lead to a very slow progress of work, lead to lot of images. Also, it will lead to very small parallax which can have problem in finding out the heights of objects. So now let's understand the drone flight over the region of interest. So first it starts with the takeoff point. So it's a specific location on the surface where the drone begins its takeoff to become airborne, and this is designated as the starting point for the flight. Then we have waypoints, and drone only flies from one waypoint to another waypoint in a straight line, and that straight line is known as the flight line. So we need to give or specify these specific geographic locations which will be used as reference point for navigation. So there is a set of waypoints which are available in a flight plan. After this, we have the region of interest with the width of W and length of L. And then first of all, as we just discussed, first of all we have to define the waypoint. So these waypoints are shown in yellow, and drone will follow from one waypoint to another waypoint in the flight line, and they are known as flight line 1, flight line 2 and so on. This is how they are labeled. So this specific pattern in which drone is flying is known as the lawnmower survey grid. This is not the only pattern in which drone flies for drone survey. There are also other survey grid patterns, and we'll look at them later on. Then after this, we also have a rally point. So let's say your drone, while it is flying over the flight path, these flight lines, it loses GNSS connection, or maybe it goes in some unexpected area. Then in that case, to prevent that from happening, a rally point is set, which is a georeference waypoint that serve as an intermediate safe location for the drone to return to in case of some emergency, ensuring controlled recovery and safety. So it is also always a good idea to define rally points. Then finally, we have a geofence around this region of interest. So this is that region and outside which we do not want the drone to go outside. So it is a virtual boundary created around a specific geographical area. So if the drone flies into or out of this predefined zone, it will trigger a specific action. For example, it can return to the launch point, it can maybe hover in place, or it can go to the rally point. So far we have seen how overlapping photographs can be used in the flight plan. But at the same time, there are also errors which are generated in the position of these images because of the drone setup, because of the lens which we are using. So one of the systematic errors that we often face in a drone setup is the lever arm offset. It is a fixed physical distance and directional vector between the drone's GNS antenna. So GNS antenna is usually on top of the drone, and camera's perspective center. So that GNS antenna is giving the position of the antenna while the camera is located somewhere else. So this creates some issues in the photogrammetry later on. It creates issue in the structure from motion algorithm which we'll apply later on. We also have another systematic error called the bore sight offset. It is the angular misalignment between the drone's inertial measurement unit coordinate frame and the camera's coordinate frame. So inertial measurement unit, the IMU, may be in the flight controller or in that place, and its angular orientation may be different from the camera's angular orientation, causing this kind of offset. In addition, we also have a bowl effect, in which even if a real world surface is flat and horizontal, but in the digital surface model that is generated from the drone images, this flat surface, it appears like a dome. So it is caused by accumulation of distortions, such as in the camera lens radial distortion. And all these systematic effects, they can be overcome by including ground control point that help constrain the digital surface model. So ground control points, they georeference the image, they correct for systematic errors, and they act as weighted constraints in the bundle block adjustment. So they refine the camera's exterior orientation parameters beyond the initial RTK PPK values received from the GNSS. And GCPs are placed at project periphery, corner, and across elevation changes to control model deformation. For example, in this image on the right, we can see one such ground control point shown by this checker box. And the flight path must be so designed that the flight path is able to capture each GCP in 2 to 5 overlapping images for robust geometric triangulation, and separate GCPs for model adjustments and independent checkpoints for unbiased accuracy assessment may be used. So finally, we have this flight plan over our region of interest. So you can see we have the takeoff point, and this is where the drone goes. Then we have a lot of waypoints shown in yellow color. Then the drone follows the flight line between the waypoints. There are also exposure stations on the flight lines, and these exposure stations have been arranged in such a way that they enable the front overlap. Also, the flight lines are arranged, the distance between the flight line has been arranged in such a way that there is side overlap between the images. Not only that, we also have ground control points which are spread in this region of interest. So airbase and distance between the flight line is such that sufficient overlap and side lap is achieved. Now we often want to know how many photographs will be acquired in flight plan based on the overlap and the flight path. And why do we need this? Using the number of photographs, we can estimate the total flight time based on the shooting interval and the drone speed. We can also estimate the number of batteries or flights needed to cover the entire area. So let's see how in a flight plan the image overlap is related with image scale and total number of images. So the total number of photographs in a flight plan is given as the number of photos per flight line and number of flight lines. So number of photos per flight line can be given as the length of the flight line divided by the airbase. So airbase is the distance between successive exposure station plus 1, and this gives the number of photos per flight line. And number of flight line is given by the width of the survey area divided by the space between adjacent flight lines plus 1. So let's look at this through a numerical to better understand this. So the numerical is calculate the number of flight lines and photographs required to cover an area of 11 km length and 5 km width with 60% overlap and 30% side lap. Required scale is 1:4800 with 230 mm sided square photograph. And we have earlier already learned how scale and ground sampling distance are related to each other through sensor size and number of pixels in a photograph. So total photographs is number of photos per flight line into number of flight lines. So number of photos per flight line, as we just saw, is length of the flight line divided by the airbase plus 1. So length of the flight line we already know is 11 km. However, what we don't know is the airbase. But you should recall at this stage that we discussed earlier that airbase is equal to the non-overlap portion on the ground. So since overlap is 60% portion, so non-overlap portion becomes 40%, and the length of the of the 230, so the photograph, the length of the photograph is 230 mm, and based on the scale we can calculate what is the length of this photograph on the ground, what is length covered on the ground, and based on the length covered on the ground, 40% of that is equal to the airbase. So we have the scale, we know the photo distance, and we want to find out the ground distance. We can put these values and the ground distance comes out to be 1104 meters. And the airbase is equal to non-overlapped percentage of the ground distance. So non-overlap portion is 40%. So 40% of the ground distance, which is 1104, is equal to 441.6 meters. Thus, the number of photos per flight line is equal to 11 kilometers divided by 441.6 meters plus 1, which is equal to 25.9, and we always round up, so it becomes 26 photos in each flight line. And the number of flight lines is equal to width of land divided by W plus 1. So we know the width of the land in this case is given as 5 kilometer. However, we do not know what is the spacing between adjacent flight lines, which is W. So number of flight lines is width of land divided by W plus 1. What we know, however, is that the spacing between flight lines is equal to the portion which is not overlapped multiplied by the ground distance. So the ground distance based on the scale photo distance, it can be calculated as 1104, and the portion which is not overlapped is 70%. Therefore 70% of 1104 will give us the spacing between adjacent flight lines. So this is equal to 772.8 meters. Thus, number of flight lines becomes 5 kilometer divided by 772.8 plus 1, which is equal to 7.47, or we round up. So this becomes to equal to 8 flight lines. Therefore, total number of photographs become equal to 26 into 8, which is equal to 208 photographs, which are required to cover this area of 11 kilometer by 5 kilometer. In addition to this, we can also control the camera angle, which is the angle between the optical axis and the vertical direction. Optical axis is the straight line passing through the geometric center of lens and perpendicular to the image plane. And this camera angle is crucial for capturing data depending on the intended application. For example, if our intention is to only create 2D orthomosaic maps and digital elevation models, then the camera angle kept as in the another direction, in the 0 degree direction. However, if you are interested in capturing the sides of the building, which is essential for creating detailed and realistic 3D models, in that case camera angle is kept oblique, with where it is between 15 degree to 45 degree. And surveys often also combine images from both nadir camera angle as well as oblique camera angle for comprehensive data capture. When we have an oblique camera angle, then the survey grid also changes. For example, we already saw a lawnmower survey grid. It is a very simple grid where the drone will go like this. It will just follow a pattern of a lawnmower. For example, if you have to clean a lawn, then the pattern that you will follow to clean the lawn. But that is not the only pattern. There is also a cross survey grid where it is kind of two lawnmower patterns superimposed but rotated with respect to each other. And then there is also a spiral survey grid pattern where it may be like this. The drone may fly like this. So which survey grid pattern to use? It depends on what is your objective and what kind of efficiency is desired and what kind of accuracy is desired. For example, if our goal is only to go for 2D mapping over open flat terrain, then lawnmower is very good. It minimizes the flight time because it takes very fewer number of turns, and it is ideal for orthomosaics using vertical images. However, if we want to map 3D objects, for example tall buildings, or if an area which has steep terrain and where very high 3D accuracy is required, in that case we go for a cross survey grid. So it has highest accuracy for 3D mapping, but at the same time it has low efficiency because the drone flies the entire area twice. On the other hand, if we just want to map a single object from multiple angles and with a very high three-dimensional accuracy, then we go for spiral survey grid. So it is very inefficient for large data, but it provides very accurate map once if you have a single object like a tower or a water tank. Then apart from the parameters we have discussed so far, the winds affect the direction of flight, and this is one of the most important parameters that comes into play and which is often not easy to predict beforehand. So because of the wind, even if we expect the flight line to take place like this, there will be a drift if the wind is coming from, let's say, the right direction. So this drift will cause a lateral shift of the drone from the flight line. And when we are trying to control, or when we are trying to overcome this effect of the wind on the flight line, which is resulted into the drift. So when we want to counteract the drift, we perform a controlled adjustment, which forms an angle between flight line and edges of photograph in the direction of flight. It reduces the effective width of the photographic coverage. So width of the photographic coverage is more in the normal flight line compared to in the crab, which is a corrected flight line. Now flying crosswind will result in stable and consistent flight path because it will give us a uniform ground speed, and therefore it will give us uniform image spacing. And wind speed lower than 2/3 of drone's maximum flying speed is considered to be ideal for taking air photos. And what happens if we exceed the drone's operational limit? It can cause instability and also cause crashes. In addition to this, there are some environmental and airspace constraints that we must keep into account. For example, there can be heavy precipitation in the form of rain, snow or fog, which can damage electronics or it can obscure the imagery. Lately, even air pollution is becoming a problem during drone survey. There can also be extreme temperature, which reduce the battery performance and flight time. And we also always strive to avoid shadows. For example, long shadows which occur using morning and evening, they cause non-uniform illumination. At the same time, we also need to be mindful of the airspace constraints, which are in the form of no-fly zone, in the form of geofencing, in the form of regulations. So in India, adherence to DGCA's digital sky platform for approval and zone awareness is mandatory. And before every flight, we should check the status on the digital sky platform. We should avoid the airport, military installations and critical infrastructure, and we should always maintain a visual line of sight with the drone. So it requires an unaided visual contact with the drone. So it limits the maximum range of a flight that can take place. In addition to this, unaccounted terrain undulation or GNSS denied environment can also trigger an emergency landing or flyaway of the drone. So finally, this shows an example of a flight plan using Mission Planner software. So in this flight plan, there is a takeoff point in the center. There are waypoints shown in the ends, and connecting the waypoints are the flight lines. They are the flight lines. In addition to this, there is a region of interest formed by the red boundaries. There is also geofence shown in the purple, so drone will not go outside the geofence. And there is also rally point for the drone to go in case of some loss of signal happens. This is another flight plan example using Mission Planner software, and for this flight plan, we can see the software has calculated the area based on the region of interest, the distance traveled based on the length of the flight lines, the distance between the images or distance between the exposure station, also known as the airbase, also the ground sampling distance, which is 3.08, the total number of photographs which are taken in this flight plan, the number of strips or the number of flight lines, which is equal to 6, footprint of each photograph on the ground, which is the size of the photograph, the distance between the lines. So this distance between the line is 49.28. Then based on this and based on the flying velocity, what is the flight time of the survey, what is the time elapsed between every photograph, which is 2.31 seconds, and the turn diameter is 20 meter and the ground elevation variation is between 266 to 277 meter. So, all these parameters are generated by the flight plan, including the flight path itself to be followed. So, in summary, flight planning helps achieve UAV survey with desired data, ground sampling distance and geospatial accuracy, and it does so efficiently by minimizing flight time and battery consumption while also ensuring safety and regulatory compliance. So, thank you very much and we will meet in the next lecture.